Well, hi everyone, welcome back. Good morning. Hope you're all excited. Today is like the final day of the program, and we have an amazing speaker with us today. And let's get started. So today we have with us Dr. Javier Lopez Piqueres, who is an applied research scientist at JPMorgan Chase and a researcher in quantum computing and condensed matter theory. His work bridges theoretical physics and practical computational challenges, particularly using tensor networks for machine learning and optimization. He got his PhD in physics from the University of Massachusetts Amherst in 2024, focusing on quantum chaos and hydrodynamics. So today, Dr. Lopez Piqueres, he will be talking to us on how tensor networks, which is a tool that is like, it's rooted in quantum physics, and how it can be, repurposed as a powerful quantum-inspired method for tackling constraint combinatorial optimization problems. And I think this is a fantastic session, that fits in so well with what we have discussing so far in the rest of the program. It's great to see how like these ideas that are inspired from like quantum mechanics, they're already making an impact on classical computing, right? And it's going to be really exciting to learn more about it. Yeah, over to you, Javier. Yeah, very excited to have you here.
Yeah, thanks so much, Avinaya, for the presentation. So let me try to start sharing. I guess you guys can see my screen. Yeah. Okay, cool. So I guess from what I've been told, this is the only non-quantum computing presentation. I'll try to motivate this from the perspective that tensor networks are a quantum computing adjacent technique, quantum-inspired technique, as some people call it. I think it's very promising as a tool for solving combinatorial optimization problems, and to what this talk is concerned, I think it promises, it's highly promising in the context of constraint combinatorial optimization problems. And so I'll be discussing these two works here. The first one is about solving constraint combinatorial optimization problems subject to equality constraints. And the second one is an extension of the first work for when solving the more general case of inequality constraints. So let's dive in. So the plan for the talk today is I'll first present a motivation for why we care about these sort of problems and why in particular we care about hard constraints, because this is what makes optimization often hard. I'll go next to give an overview of how normally people deal with constraints in standard methods. I'll give a brief introduction to tensor networks and then discuss related work in the space of tensor networks for combinatorial optimization. And then the bulk of the talk will be in the next two parts. The first part will discuss tensor networks for equalities. Here, the idea is that symmetries, which are a core concept in physics and quantum computing, or quantum physics specifically, can be used as a source of inspiration to deal with equality constraints. And then the second part is about how to extend this formalism based on symmetries to handle the more general case of inequality constraints. And then the key concept here is quantum regions, which I'll describe more in detail later. And finally, I'll wrap up with some summary and outlook for future work. So yeah, let me start with why we care about combinatorial optimization, and specifically constraint combinatorial optimization. By now, I'm sure, given how many talks have been given about combinatorial optimization problems, it's not, I don't need to justify why we care, but let me just briefly mention what we mean by constraint combinatorial optimization problems and where these problems appear in practice. So the idea here is to pick the best combination of yes/no choices, but where only certain combinations that obey some rules count. So a very popular example is in the context of portfolio optimization, where the idea here is that you want to maximize the returns or minimize risk subject to choosing K over N assets. So this is what's known as a cardinality constraint. A perhaps more familiar one is the knapsack problem, where the idea here is that you want to pick the most valuable set of items, but where the total weight stays under a capacity. And this is an inequality constraint. And we also have examples in logistics and scheduling. And really the common shape of all these problems is that we want to minimize a cost function, here C of X, subject over binary variable, subject to either equalities or equality constraints or inequality constraints. And it is precisely, even for when the cost function is linear, the mere presence of these constraints is what makes these problems very hard to solve. And so if we find a way to deal with the constraints in an efficient way, in a systematic way, then we would hope to solve the whole problem perhaps more efficiently than more efficiently. And so to give an intuition why these types of problems are hard, it's helpful to think of the space of all possible bit strings of fixed size n. So of course there are 2 to the n number of bit strings, but once you include constraints, only a tiny feasible region in general are possible, here shaded in orange. So we only care about bit strings living in this small region. However, this feasible region can still be exponential. And so brute force and random guessing are not going to work, because we're searching over an exponentially large space, but the feasible space is also very, very tiny, even though it can be still exponential. And so this is what leads to the question that drives the entire talk, is namely, can we build a model that can only propose feasible solutions? And the idea is that, in fact, tensor networks can provide a feasibility condition by construction. So we can basically construct tensor networks, which I'll describe in a moment, in such a way that they only produce feasible bit strings. And this can be done efficiently for very natural types of constraints. So before that, let me discuss how the standard methods deal with constraints. There are 3 broad categories of types of ways in which methods deal with constraints. The first one is, which is very popular in quantum computing, is to add a penalty term into the cost function, into a usually quadratic cost function, or QO type cost function. The issue with this approach is that, for one, you introduce an extra hyperparameter, lambda, which is sometimes hard to tune, and the feasibility is not guaranteed. Moreover, when you include multiple constraints, then you include multiple such lambdas, and the problem becomes all of a sudden overparameterized. Even more, this is for equality constraints. Dealing with inequality constraints, to my knowledge, is very hard to put into a QO form, into a quadratic form. So that's one approach. The second approach is to do some sort of like relaxation of the integrality constraints. This is done usually in methods that try to convexify the already non-convex problem and then run back. So one example is the branch and bound type class of algorithms that precisely do this. They relax the integrality constraint and then do some sort of like branch and cut method to recover the integer feasible solutions. So this works very well in practice, especially for linear cost functions, but it doesn't work as well for nonlinear variants, or even like black box cost functions that we may care about. And finally, the least preferred option is to just generate samples and hope for the best, hope that we will land in the feasible region. Of course, when the feasible set is pretty large, this doesn't scale well. So the common thread across all these 3 types of ways of handling constraints is that the model can still propose invalid states, and we don't want that. And so this is what motivates this work, namely, can we build the constraints directly into a model? And tensor networks allow for this, as I'll show. So what's a tensor? Let's start with that. It's just basically a multi-index array, and there's a very nice way of depicting tensors in the context of tensor networks, which is to depict a vector with one leg and a box. Similarly, a matrix is a box with 2 legs. A rank 3 tensor is a box with 3 legs. And when you connect to such tensors, that means you are summing over the shared index, which is known as a contraction, and we depict it in the way here shown. A tensor network is nothing more than a bunch of such tensors connected by contracted legs. Perhaps the most popular type of tensor networks is known as the matrix block state, or MPS for short, which is a one-dimensional tensor network, where each local tensor is parameterized by a variable xi, which will be our binary variables. So when you contract this tensor network, this MPS, this gives us a number for a given bit string, here x1, x2, x3, which is it's just nothing else than the amplitude for a given, in the context of relating to quantum physics concepts, this is just an amplitude for a given configuration. And its square is a probability. A key concept here is the bond dimension, which is if we can view these blocks as for a fixed bit as a matrix, the bond dimension is just the rank of that matrix, the number of rows and columns of that matrix. So one way to construct a probability distribution out of an MPS, also known as a Born machine, is precisely to square these amplitudes and then normalize them so that they sum to 1. And so one nice property of tensor networks is that, especially this type of tensor networks, MPS constructed in this way, these warm machines, is that one can sample efficiently from this type of distributions. And the goal for us would be to represent a tensor network such that only feasible bit strings are allowed, and the remaining bit strings, those that are infeasible, correspond to amplitude equals 0. So they don't contribute. So before our work, there was a few works that had explored tensor networks for combinatorial optimization problems, but for what I call local constraints. For instance, this one on the left, they tackled what's known as the open pit mining problem, which is a nice physical problem where you have the property of locality where constraints are locally coupled. This gives rise to a two-dimensional tensor network. And once you construct this constraint tensor network, you can find the optimum via imaginary time evolution, which allows you to find the ground state, which is very similar to how people solve constraint combinatorial optimization problems in quantum computing. So this is the one on the left. The one on the right is about also dealing with local constraints, but in this case, the authors cared about enumerating solutions and things like that. The important thing is that the type of constraints they dealt with are local. Familiar examples of local constraints are SAT type constraints, independent set, coloring vertex cover, and so on and so forth. So, the thread for this talk is about global constraints, and not just equalities, but also inequalities. And many constraints of practical relevance fall into this category. I mentioned earlier cardinality, budgets, capacities, bounded assignment. One thing to mention also is that if we are able to find a way to handle global constraints, as a concrete example, we can also deal with local constraints. So it's a more general approach. And the two works I'll be discussing today, as I mentioned earlier, one is for equalities here on the left, where the idea here is that these equalities can be mapped to a problem about symmetries, specifically U1 symmetries, and for which people in the physics literature had already developed a formalism to represent tensor networks as U1 symmetric states, and where here basically the intuition is that these symmetries, or the most famous type of constraint, which is cardinality, is exactly the conservation of particle number, which is the most famous probably quantum symmetry that there is for quantum states. And so to our knowledge, what we did was basically extend this formalism to arbitrary number of equality constraints where the coefficients can be different from 1. So it's basically extend this U1 symmetric tensor networks to deal with any kind of equality constraint. Again, where X, of course, is over binary variables. And then the work on the right, we extend this formalism to, inspired by symmetries, by quantum symmetries, to inequality, to handle inequalities. And this is where the concept of quantum region comes in, which draws inspiration with a key concept in the context of U1 symmetric states, which is the charge of a state, which I'll discuss in more detail later. And also, to our knowledge, is also the first time that people were able to construct in a systematic way tensor networks that fulfilled inequality constraints, global inequality constraints. So the question then, once we've constructed this tensor network, this constraint or symmetric tensor network, how do we optimize? How do we find the optimum within this feasible region? And there are multiple ways of doing this, but the approach we followed, it's inspired, or really taken from this work here, it's called the GU algorithm, or generator enhanced optimization algorithm, which is a data-driven approach where, starting with from some sample data points, you try to learn progressively what are the regions of the space that correspond to low cost regions. And I'll also describe more in detail how this works. And this is in contrast with the more popular approach in quantum computing, which is just to do some sort of imaginary time evolution. And also to mention that there have been some follow-up work in this space. One here I want to mention is this one here, where the approach, they also tackle global inequality constraints, but in in a different way, and also the way they optimize the cost function is more akin to what people do in quantum computing, namely via imaginary time evolution. Okay, so that's a teaser of what the talk is going to be about, and then the next is just going to be really getting into the details of how the construction of tensor networks, symmetric tensor networks, and constrained tensor networks more generally. And yeah, so we'll start with first the case of equality constraints, because it's just easier to understand. And again, to reemphasize, the key intuition here is that symmetry it amounts to having constraints. So yeah, so here's the core idea. It's actually somewhat simple. Let's take a simple constraint like this form: x1 plus x2 plus x3 equals 2. And we're just choosing exactly 2 ones. We're going to read the bits left to right and counting the ones we find so far. And we're gonna keep the running count of the ones so far. We're gonna store the count on the bond between two tensors, L1, L2 here in this diagram on the right. And that number is what we are going to call charge. Now, different bit strings will give different counts. And so each link is going to be parameterized by a set of charges. And so these are the dots we show here on the bottom right diagram, where the y-axis corresponds to the charge and the x-axis corresponds to the links. And so starting from link 0, which is hidden here, but we should be on the left of the first tensor, after adding x1, we can either sit at 0 or we can jump by 1. Similarly, once we are here, we can either at the first link L1, we can either stay if x2 equals 0, or we can jump by 1, and so on and so forth until we arrive at the last link L3, whereby the constraint this has to be 2. So we can then read of all the possible bit strings by just counting the number of paths starting from 0, L0 equals 0 to L3 equals 2. And a simple counting reveals that is only 3 different paths can arrive at 2. And so yeah, that's basically what the charges are and how bit strings can this approach can generate all possible bit strings. The bond dimension, which I discussed earlier, which describes basically the rank of the matrix for each of these blocks, is just the number of charges on each link. And for this example, it's just 2. So this is for the cardinality constraint. For a general sum where the coefficients can be different from 1, the formalism applies the same. It's just that the coefficient will be different from 1. So why this way of depicting or thinking in terms of constraints is powerful? I think it helps to, again, look at the cardinality constraint, and we're gonna try to store all possible bit strings by just counting all possible bit strings, right? So the number of bit strings is gonna be n choose kappa, where kappa is the cardinality constraint. If we take, for example, 50 bit strings of size 50 and cardinality 25, the number of bit strings is gonna blow up. But thinking in terms of charges, we can store all these bit strings in only a number that grows linearly in n and kappa, not exponential. So for this particular example, only about 1,000 numbers we need. And the way we store these numbers is precisely by constructing this set of charges allowed for it across each link, which will induce a block sparse structure on each of these matrices. Which I'll describe in more detail in a minute. But this is basically the intuition. We can compress an exponentially large space into a model that grows sometimes polynomial in both the number of variables as well as in the constraint. So yeah, taking a zoom into these block sparse structures, let's take let's zoom in into a single tensor. So the generic interior of a generic tensor has 3 legs, right? And here the left bond is gonna carry the incoming charge. The right one is gonna have the outgoing charge, and then we're gonna have the bit that is also, it's called a side charge, which adds to the charge coming out. So basically the rule here is charge out equals charge in plus the bit. And so every interior tensor is gonna conserve the charge, and the total target is going to be kappa here in dashed line on the right of the MPS. So let's see what the conservation of charge induces on this matrix when we fix x. So when we fix x to be 0, that means the q out, the charge out, is going to be the same as the charge in. We're going to represent the matrix in terms of rows being charged in and columns being charged out. And we're going to label them from 0 to 2. So what we see is that charge conservation gives this very nice diagonal type structure. So the where the green boxes correspond to arbitrary numbers and the blank cells are just 0. Similarly, if we have the bit being 1, then conservation of charge gives this off-diagonal structure, so still block sparse, and the rest of the entries are 0. So bottom line, charge conservation induces this block sparse structure on the matrices. So this example was for cardinality constraint, but for a general equality, this same principle holds. And in fact, it carries over to the case where we have multiple equalities. It's just that the bookkeeping is just more complicated, but the same intuition holds. Namely, when we have a constraint of the type AX equals B, we get a block sparse structure on the matrices. So far I've discussed, okay, how do we construct a tensor network that represents the entire feasible space? How do we find then the optimum? And so as I mentioned, we're gonna borrow this GEO approach, which I'll discuss now. The idea here is you start with some random samples over the feasible space. So you've constructed this symmetric tensor network over the feasible space, and you're gonna sample randomly initially. And then you're gonna train, you're gonna try to bias, you're gonna compute the cost of each of these bit strings, and you're gonna try to bias the training in such a way that it focuses only on the region of low-cost samples. As long as you don't overfit, what the model is gonna do is it's gonna propose, as you train, it's gonna propose new samples that are potentially in the low cost region, but are hopefully lower of cost than what you started with. And one way to do this is to bias, to introduce a temperature factor here, where across iterations, you anneal that temperature so as to bias progressively the set of samples that you learn over as well as you sample. It will progressively concentrate on the low cost region. So the way this is done internally, and what happens basically in the tensor network is that we start with an MPS with a block sparse structure of this form where all the blocks are the same. And as you train, the mechanism by which you're training an MPS is via a series of SVDs, singular value decompositions. And what's gonna do is it's gonna adjust the size of these blocks, sometimes even like kill blocks that are not needed. And so basically this is what happens internally across all the matrices as you train progressively the tensor network. One thing to mention here is that at no point we're exploiting whether C of X is linear or quadratic. It can be black box. The only thing that matters is that you're able to sample from the MPS as well as you can find the cost for each bit string. So what does that bias in practice? Here on the left, I show the costs of training a vanilla MPS where you don't have any block sparse structure versus the symmetric case. The specific problem, it doesn't really matter which one it is, but what we show here is that for different bond dimensions, training a vanilla MPS is much more costly than the symmetric one. And this is because, again, the block sparse structure that zeroes out entries that are not needed. So you save on space as well as on time. And the one on the right, what is construct the entire feasible space for a given constraint, in this case is the cardinality constraint, how much can you recover? And what it's shown here is that if you want to use a vanilla MPS of different bond dimensions, here in different colors from 6 to 34 bond dimension, what you see is that you're very limited in how much you can recover of the entire space. Epsilon here, 0.1 is just like the 10% of the entire feasible space. You train over that 10% over the feasible space, and then here at the same, but for 1% of the feasible space. However, if we are to do this with asymmetric tensor network, we are able to basically generalize or like recover much more of the entire space. And this is because we are exploiting the structure of the constraints. As a quick aside note for why a tensor network and not maybe a neural net is that, as I alluded earlier, we are kind of thinking in terms of like symmetries, and symmetries are very tied to quantum, really, and tensor networks are inspired by quantum, so it kind of intuitively makes sense that handling constraints of the ones that we care about, global constraints, might be easier with tensor networks. But I just wanted to mention that other kinds of symmetries are perfectly handled by neural nets, and one such example are external symmetries like permutations, translations, or rotations, where there are plentiful neural network architectures that handle those type of symmetries or constraints better. But the types of symmetries we care about are internal symmetries, and these are the ones that map directly into these global constraints like cardinality constraints and and capacity constraints and all those. And the key intuition why this is the case is because of the multilinearity property of the tensor network that allows to in particular, block decompose the matrices, which is something that, due to the non-linearity property of your networks, this is very hard to achieve. Okay, so far I've discussed tensor networks for equality constraints and how they relate to symmetries. We're going to extend this intuition, this formalism, to the context for inequalities, and this is where the concept of quantum regions comes in. So let me do this in the way that we actually, in a way, discovered it, and we'll start with the obvious thing, which is not going to work, but hopefully will help building the intuition for the right approach. And so the obvious idea is we take this inequality here with a lower bound and upper bound, and we try to stack up several equalities. And so the flux, or the final link, is going to have multiple final values from L to U, the lower bound, up to the upper bound. So you could build that, but if you do, then you're going to still be tracking every single charge separately at every link. And this doesn't scale well. This is very similar if you're familiar with the slack variable approach for handling inequalities in the context of QO approaches. This is similar to that. It's not efficient. And so the fix comes really from the realization that many of these charges share the same fate. And in particular, there are three kinds of charges. Those that are safe, meaning they are guaranteed to end within the range, and we're going to merge them into a single region. We'll call a quantum region, in analogy to quantum charges from U1 symmetric tensor networks. Then we're going to have also undecided charges. Those are that still will depend on later bits. So we're not able to see if they can be bundled together or not. So we'll keep them separate. And finally, those that are doomed. So those are charges that no matter what, they'll fall. They'll give rise to bit strings that fall out of the feasible region, so we can drop them. So a quantum region is nothing more than a continuous group of such charges. So what I've described is just for one inequality where the charges live in one line. But when you include multiple inequalities, the charge is just and M is a point in a dimensional space where D is the number of constraints. Sorry, M is the number of constraints. And the quantum region now is just a box or a union of boxes, which, and as you go along the chain from left to right, what you're going to see is that the fusion rule, the Q out equals Q in plus the charge, the bit charge, what's going to do now is it's going to break down this initial box into smaller pieces. And the two key operations here are the intersection and the symmetric difference. So you're going to be basically breaking down this initial box into smaller ones. The final set of quantum regions will be found over two sweeps. The first sweep will find the potential quantum regions, and then the reverse sweep is going to discard those quantum regions that are not feasible. This is a technicality that may not be obvious from this, but as a free bonus, we get once we construct this tensor network in terms of like these quantum regions, we can contract tensor network and get the entire feasible, the number of feasible solutions. So what does this cost? We can frame this from like the charge complexity, what we call the charge complexity, which is a quantity to measure just the number of quantum regions across the maximum number of quantum regions across all links. And so we took this problem, this facility location problem, where the constraints are of this form here, multiple inequalities. And in a nutshell, what we found was that this charge complexity, the number of quantum regions, grows polynomially in n in the number of variables. Sometimes even it saturates. And but the catch is that the number of quantum regions grows exponential in the number of constraints. So there is not a curse of dimensionality, but there is a curse of constraints, at least for this problem. And then, so going back to the two different layers of how we approach this problem, first we construct the tensor network in the feasible space, and then we optimize via this GEO type approach. We took the quadratic knapsack problem, which is strongly NP hard. It's just a quadratic objective plus one capacity inequality constraint. This problem bears a lot of relevance in finance, logistics, telecommunications, and so on. And we compared this against our approach against SCIP, which is a leading solver for nonlinear integer programs. And we tried to solve this problem for various problem sizes from 50 to 400, from 50 bits to 400 bits. And the results show that our solver remains competitive for somewhat smaller problem sizes, where we see here on the percentage improvement on the left plot versus problem size. We see that the black dots, by the way, are 10 different problem different problems for the same size. So we get some statistics. What we see is that up to 100 it remains competitive, but past 200 the percentage improvement is oftentimes superior to what the SCIP solver does. But not only that, not only do we find some better samples, but we also do in more quantity, because our approach is sample based. If we look at the plot on the right, we see that whereas SIP gets stuck past a given time, we see that for our approach, we see a continuous line of multiple solutions that we find below what the SIP solver does. So to conclude, what we did today was we framed this problem of minimization of a cost function subject to hard linear constraints, and the core idea is that a linear constraint can be thought of as a symmetry or as a conservation law. For equalities, this mapping is exact. It's just given in terms of U1 churches, where we borrow this concept of symmetric tensor networks from the literature. And then for inequalities, we extend this formalism to develop this new formalism in terms of constraint MPS, where the crucial variable here is our quantum regions, which are an extension of U1 charges. And the way we optimize the cost functions via this GEO style generative loop. Worth mentioning that the cost function not need to be linear quadratic, it can be black box. And really the takeaway result is that via this approach, we found that for many problems of relevance, the costs of constructing this tensor network are polynomial in system size, but exponential in the number of constraints. We also found that the results are very competitive against the leading solver for quadratic knapsack. And finally, that we can construct, once we have this tensor network, we can contract efficiently and find the number of solutions, which can be also can be useful for certain problems. So as limitations, the one clear one is that we found that the bond dimension grows exponentially in the number of constraints, this course of number of constraints. And the whole formalism we developed, while it can be generalized to more generic tensor networks, it only works for matrix product states today. And finally, in terms of the optimization scheme that we use, it has a slow warm-up at the beginning before it overtakes SCIP. So if you care about very fast solutions, this approach might not work. For future work, one thing I glossed over is that while we can construct tensor networks from valid or feasible bit strings for equality constraints, we cannot do the same for inequality constraints. So there's not a way of from data read off what are the entire feasible bit strings for inequality constraints. Again, also generalizing this framework to higher dimensional networks like PEPs, which are two-dimensional tensor networks, and then in the context of optimization, finding better initialization strategies, annealing schedules, that would be helpful. And beyond this, in the context of physics, I think I'm also very generally interested in seeing how this approach could be useful in the context of open quantum systems, where you may have a broken or mildly broken charge conservation. So the takeaway, again, is that constraints are nothing else than symmetries, and we can encode that into a tensor network structure by construction. And yeah, that's it. Thank you. So these are the two focus papers, as well as the code for anyone who wants to try to reproduce the plots that I shared and maybe even improve over the approach presented. It's open source. I'm happy for anyone who wants to contribute to do so. And just before I conclude, as a Spaniard that I am, I can't help myself. But in 2 days, Spain is going to play the World Cup final. And so allow me to one shameless moment. Vamos, España. and here's a real kind of secret that I hope brings home for some of you that maybe got lost into the fancy formalism, which is that a tensor network is nothing but a collection of simple tensors, where now on no single tensor is special, and the power comes from how they are connected, contracted together, correlated, and the whole represents more than the sum of the parts. And so that's how La Roja Spain plays. Not 11 stars, but one connected team. All right, I'll leave it to that. And thank you for your attention. And I'm happy to take any questions.
Yeah, Javier, thank you for this amazing talk and the fun slide at the end. Yeah, good luck to Spain in the finals. Yeah, we have a bunch of questions. I'm gonna go over them. First question from Yagna. So as optimization problems become increasingly complex, do you believe that the next major breakthrough will come from fundamentally new algorithms, or would it be from integrating optimization with AI systems or something else?
Yeah, that's a really good question. I think it's going to be a bit of both. I think, what AI has taught us is that, sometimes having like these systems are so powerful that they can solve, not just IMO level problems. I'm sure they will also be able to solve very hard NP hard problems. But I do think that that will also come with along with progress in more structured approaches like tensor networks. So tensor networks are, arguably a more structured approach than just throwing a neural network to for solving a problem. As I argued earlier, like constraints, for instance, right? Like if you have a way to leverage or exploit constraints in a way that I think that can help solving the problem. And I think tensor networks is definitely one such a way. So I think it will come in both ways, like both AI as well as more more boring or even fancier math. And I do think that tensor networks will play a key role there.
Thank you. Another question from her. So your work bridges local and global constraints elegantly. Do you think this framework could eventually serve as an unifying representation for optimization across both classical and quantum machine learning models?
Yeah, so the connection with tensor networks, I mean, I do think that, yes, there can be a general approach for any constraints. I have doubts that maybe nonlinear constraints may be able to be addressed with tensor networks, but that's an open question. But if we talk about linear constraints, yes, tensor networks, I think, provide a very general setup. How you marry this approach, handling constraints with tensor networks and ML models, that's an open question. And to this day, I don't know if like that's something that could be feasible, frankly. Like there are some incompatibilities there in that neural networks being nonlinear models make it very hard to marry with precisely what tensor networks are, which are multilinear models. But more broadly, this is just one approach to handle a specific type of combinatorial optimism problems, which are those that have constraints. I'm sure AI, less sure about quantum AI though. I'm sure AI can help in solving or use a subroutine of other optimization problems like if I can think of reinforcement learning techniques for just finding the best way to branch in the context of branch and bound methods. I know people have used both RL as well as generative AI techniques to find the best nodes to branch off. So I think AI for combinatorial optimization, yes. AI for constraint combinatorial optimization, yes, but with tensor networks, not so sure. And then quantum AI, I don't know. That's an open question. I'd love to be, I'd love to see progress there, but to this day, I don't know if quantum can help so much there.
Thank you.
Yeah.
Question from Sriram. What are the main advantages of encoding constraints using symmetry instead of penalty terms in Kubo?
Yeah. So I think definitely the drawback of including penalty terms is that you include extra parameters that you have to tune, this lambdas. So that already poses a challenge, especially if you have many constraints. The more constraints, the more parameters you have to tune. And then I think probably the biggest roadblock is handling inequality constraints, which, as I mentioned, my understanding is that people that do Cubo do this slack variable approach where the number of variables, the number of bits that you have to include increases with the problem, with the size of the constraint, the size of the gap of the upper bound and lower bound, and so there are tricky things there to do. Whereas this approach, I guess with tensor networks is feels more natural in that you're able to encode constraints in a more systematic way, and there are no free parameters. But as always, I'm sure like there will be problems where the QO with penalty terms works just better than a tensor network, and so. But as a proof of principle, I do think that the QO has drawbacks that the tensor network approach can ameliorate.
Okay. Got it. Thank you. Question from Sunil. Under what conditions do you choose between the symmetry tensor network and constraint tensor network, and which one is more reliable?
Sure. So yeah, the symmetric tensor network is a very specific, I guess, model for just equality constraints. And again, we called it symmetric tensor networks in analogy to U1 symmetric tensor networks that people had used in the context of quantum physics for solving problems with a symmetry, with a U1 symmetry, global symmetry, like conservation of charge. But constraint tensor networks is what we call the more generic term for inequality, and it's any kind of linear constraint, including equality constraints. So really, constraint tensor networks are probably will be the go-to architecture, and this is the one that we include in the report here. So this is if you want to get familiar with what it is doing, I encourage people to take a look at the code repo. But in a nutshell, constraint tensor networks are just a more general tensor network than symmetric tensor networks.
Thank you. Question from Dana Lakshmi. Why is imaginary time evolution used instead of real time evolution for optimization problems?
Yeah, so this is right. The idea is that you want to find the ground state of a problem, and by doing imaginary item evolution, you're able to dump those. If you think of a vector expressed as a linear combination of vectors, what imaginary item evolution will do is just, starting with the equal superposition of all states, what we'll do is just dump those states that are of higher cost. And if you do this very slowly in imaginary item evolution, you are guaranteed, unless there are some pathological or some constraints in how this is guaranteed to be the case, but you are guaranteed to converge to the ground state in many cases of practical relevance. So that's what imaginary item evolution does. It just dumps, because you have a temperature. Think of imaginary time as temperature, basically, rather as the inverse of the temperature. What this is going to do is just, as you lower the temperature, it's just going to find the ground state, which is ultimately the lower cost bit string for your problem.
Thank you. Question from Vishal. If they want to apply this framework to a new optimization problem, what should be the first step? Yeah,
right.
should it be like, yeah, I can finish the question. Should be by identifying conserved quantities, deriving the tensor network, or analyzing the constraint graph, or something else?
Yeah. A good question. Definitely, the first step is to make sure that the problem statement fits into the problem category that these tensor networks can solve, which are the cost function can be anything. While our approach can be generalized to integer valued variables, if we think of bit strings, then the cost function can be anything, but the constraints have to be linear. That's really the only thing. And then the other thing to bear in mind is there shouldn't be that many global constraints. And this is because of the cursive number of constraints that I mentioned. This can blow up the cost to initialize the tensor network. But it can also work for many local constraints. So if you have many local constraints, this approach is also perfectly valid. Other than that, it's pretty general. Of course, there are caveats, and depending on the nature of the problem, it might be more suitable or not. But generally, I think what I would be looking for is a very complicated cost function for which you're just throwing away the standard methods like branch and bound. So if it's the more nonlinear your cost function is, the better you're placed, and then the constraints have to be linear. Yeah.
Oh, thank you. Yeah, we're almost out of time, and I want to be mindful of your time, Javier.
I'm
Maybe
happy
we
to
can
take
take
a
one.
couple more questions if needed. Like, yeah.
Okay. Okay, that'd be great. Yeah, we have
Yeah.
like 3 more questions, so I can just go through
Sure,
them.
I can do that. Yeah.
Okay, thank you. Question from Dhanalakshmi. So which type of optimization problems do tensor networks outperform classical optimization methods in? And what role does the block sparsity play in reducing the memory and computational cost of the MPS?
Yeah, that's a great question. So yeah, I think that ties back to the previous question on like what problems are, when should I be using this approach? I mean, needless to say that, people should, I might be biased and like, I've worked on this long enough, but I do think any problem where the cost function is nonlinear, preferably black box, and the constraints are linear, that is a very well suited problem for this approach. There shouldn't be that many global constraints, as I mentioned, because of the cursive number of constraints. And as far as the block sparsity, how that plays a role in saving costs, you should think of a matrix as a n times the number of entries, where n is the number of rows, m is the number of columns. If you are zeroing out certain entries, then the number of numbers you have to, the set of numbers you have to store is just fewer. So it comes with just like the nature of the matrix you're working with. It just has more structure, and that also carries over to the time. So you are able to, if you exploit sparsity, you're also able to handle these matrices in a more efficient way.
Right. Yeah, thank you. So for students who are new to tensor networks, what would you recommend learning first?
Okay.
Question from Parvati.
Yeah. So, I mean, one thing that comes to mind is the first reference. By the way, the 2 references are open source references. So you should, once you look this on Google, you should be able to get free access to the references. I do cite references for tensor networks, like very basic tensor network references. That would be one way. And also nowadays, with ChatGPT and people can learn very easily about concepts like this. So that's also another approach.
Yeah, thank you. Question from Vishal, and we can wrap up with this one. You showed that symmetric tensor networks are very effective when constraints can be expressed as conservation laws. And so what has been the biggest challenge you have encountered with this approach? And for optimization problems where that symmetry doesn't naturally exist, what alternative tensor network representations would you explore?
Yeah, so as far as like what types of constraints, so the method is generic enough that it can work for any linear constraint, as I mentioned. I guess the caveat there is of course, there's a dependence on the coefficients, like the A matrix, for instance, how well structured that matrix is. If it's very random, you would expect the tensor network to not be efficient. So the more structured there is, the more the simpler it gets. As a very extreme limit, the cardinality constraint is the simplest constraint because it's all ones. And as we saw, the efficiency is very, it's very good. Like you have an exponentially number of feasible bit strings, but this can be compressed down to very few numbers corresponding to the blocks of the symmetric tensor network. So that's really like the punchline. You don't have to think in terms of symmetry so much. The symmetry is more of like an inspiration really for us to develop this framework, but it just works for any constraints. And I'm one thing I would encourage is in the repo you can just plug in. It has a very simple way to plug in constraints. You can just try fitting in a constraint and see if like you get within reasonable time the tensor network. And yeah.
Yeah, thank you so much. I think that was the last question. Thank you so much for taking the time to come talk to us today, Javier. I really appreciate it. And thank you for sharing your wonderful work. I think these tensor networks are such a powerful concept, and I kind of see them kind of coming up in various different applications. So it's kind of really useful for our participants to like learn so much more about this topic.
Yeah.
And yeah, thank you so much. And thank you for staying over time.
Yeah, of course. I'm happy. Yeah. Thank you, everyone. Bye.
Thank you. Bye.
Thanks, Javier.